Hi guys, welcome back. In this video, we are going to talk about electrical transformers. Okay, and we're going to see how they are similar to gear chains in mechanical systems. Okay, let's get into it. So before solving this problem, I want to talk a little bit about transformers in general. In chapter 1, we define transformers as elements that connect the effort on the first side to the effort on the second side with a constant number. Yes, I'm going to call this constant number as a square. Okay, and we also mentioned that in these transformers we have another property, that the flow on the second side, or the flow that you get from them, is in fact the same constant number multiplied by the flow on the first side. And what did we mean by effort and flow? Effort was anything like force, and flow was anything like velocity. Yes, for example, in gear chains, if you guys remember, and 1 and 2 would be the number of gears, okay, on gear 1, and the number of gears on gear 2. Okay, let me just bring N2 here. You notice that if you have effort as the torque on the first side and the effort as the torque on the second side, then this equation for the transformers would say that effort 1, which is T1, equals to some constant number multiplied by effort 2. That constant number in gear chains turned out to be N1 over N2. Similarly, if you assume that you have omega 1 here, or theta dot 1 here, as the angular velocity, which is the flow on the first side, and theta dot 2 here as the angular velocity, which is the flow on the second side, then you have the same constant number, N1 over N2. And on the first side, you will have, on the left side, you will have the flow on the second side, and on the right hand side, you will have the flow on the first side. Okay. And how did we get these numbers, basically, these equations? Well, we said that in transformers in general, there is one specific assumption, okay, that these guys are power conservative, which means that the power that you provide to them is the exact power that you harvest from them. Yes, okay. And with that in mind, we had such a thing, okay, we had such a thing that the power was effort multiplied by flow. Okay, so if you consider the power on the first side as E1 multiplied by F1, which is the effort 1 and flow 1, it's going to be equal to effort 2 and flow 2. Yes, okay, so in gear chains we had T1 theta 1 dot equals to T2 theta 2 dot. Okay, so now let's look at some other transformers. Okay, for instance, another transformer that we have is the electrical transformers. Okay, you have two coils of wire basically adjacent to each other. Okay, that if you provide some E1 on the first side, okay, this E1 would be transformed and induce another voltage on the second side. Okay, so I'm going to call the voltage on the first side as E1, the voltage on the second side as E2. Also, I'm going to call the current that passes through the first side as I1. The current that passes through the second side, I'm going to call it as I2. Similar to the gearboxes, okay, we have similar concept. The effort on the first side, which is the force kind of character in electrical systems, our effort, we mentioned that it's the voltage. It's going to be equal to some constant number multiplied by the effort on the second side. Okay, and it turns out that that constant number would be again N1 over N2, which is the number of windings on the first transformer over the number of windings on the second transformer. Similarly, we have very similar concept with the flows. The flow on the second side, which is I2, equals to the same constant number, I1, the flow on the first side. Okay. And in general, if you look at them from the energy perspective, you see that electrical transformers are just like gear chains. They're just like rack and pinion. They're like a lever. Okay. These all are examples of transformers. Okay. And in these transformers, what you guys need to remember is the underlying assumption here is that they are power conservative. They do not consume power. They do not store power. They just transform power from one side to the other side. Okay. And the equations that govern all these transformers are the ones that we have here. Okay. Let's get back to the example that we have. Let's talk a little bit more about the electrical transformers. In electrical transformers, based on the voltage that you have, okay, on the first side and the second side, okay, and the number of windings, you can have three types of transformers: step up transformers, step down transformers, and isolation transformers. The difference between these guys is the number of windings over here. So, with this introduction, guys, I'm gonna get back to the example that we were solving. So, I'm gonna summarize what I knew about these transformers in here. I know that if I have the voltage on the first side of this transformer as E1, this is going to induce another voltage on the second side as E2. And I know that there is a relationship between E1 and E2. E1 is equal to N1 over N2 E2. Similarly, if you look at the input current of this transformer on the first side as IL, and let's say that I'm going to call this the second current as IC here, okay, because IC is the same current that passes through through the resistor and the capacitor, okay, then I would know that IC also has a relationship with IL, which is N1 over N2 IL. Yes, where did I get these equations? From the general behavior of transformers. Okay. Now, let's go to our 4-step approach to model this system. Okay, so in step 1, I'm going to write down the elements and the circuit. Okay, and for this circuit, what I'm going to do is I'm going to have them as inertia, stiffness, friction, and I'll look into my sources and the number of ODs. Okay. So, do I have any inertia element in this system? Well, look at this. I have L here. Yes, this is my inductor. How about the coils here? Should I consider inductance for these guys, each of them? What do you think? In another way, when we were talking about the gear chains, did we consider any moment of inertia, which was the inertia element in mechanical systems, for any of the gears? Can you guys remember? Well, did not. Yes, because our underlying assumption was that these guys are power conservative, which means that they do not have any inertia and they do not have any stiffness. So, or any friction. So, we do not consider any inertia for these guys. This is not an inertia element. Your only inertia element is the inductor. Similarly, For a stiffness element, I have one capacitor here, which is this guy. Yes. So for the capacitor, I would have, for the stiffness, I would have the capacitor. And at last, my friction. Yes. So for this friction, I would have my R element. Okay. The source for this problem is ET, which provides the effort, which is the voltage. And at last, I need to comment on the number of ODs. Okay, look at this. I have 1 and 2 energy storing elements. Yes, so I would need probably 2 ODs. Okay, so let's go to our problem, okay, and see what we have here for dynamic variables. I would go to step 2 and I would list my dynamic variables. Okay. For dynamic variables, we are looking at 2 things. First, the voltage across the capacitors, which we show them with EC, and then the currents through the inductors. I have 1 capacitor and 1 inductor, so the voltage across that capacitor and the current through that inductor are going to be my dynamic variables. Next, I'm going to go to step 3, okay, and I'm going to write down the ODEs for each of those energy storing elements. Yes, so write down ODEs for your energy storing elements. Okay, so once again, I have the inductor EL equals to L I dot L, and I have the capacitor C E dot C equals to IC. Let's call this equation as equation Smiley and this equation as equation Cyclope. Again, guys, we're gonna label these terms as good and not good. For us, whatever that's dynamic variable and input is a good term. Whatever that's not dynamic variable or not an input, it's not a good term. Yes? So let's look at the first equation, equation Smiley. I dot L is the time derivative of my dynamic variable, IL. It's a good term. EL, on the other hand, is not my dynamic variable. It's not my input. It's not a good term. Yes? Okay. Similarly, E dot C in equation Cyclope is the time derivative of my dynamic variable. It's a good term. And at last, IC is not my dynamic variable. It's not my input. It's not a good term. So my job is going to step 4 and rewrite not good terms with the tools that I have, which are, by the way, KVL, KCL, and Ohm's law. Yes? So let's go to a step 4. And in step 4, rewrite not good terms using KVL, KCL, and Ohm's law. Okay, cool. Look at this problem. How can I write KVL and KCL and Ohm's law? Let's go ahead and dissect these 2 parts of the circuit. So I'm going to cut it from here. Okay. Then if you do that, you see that you have one loop on this side, one loop on the other side. Yes, so you can write 2 KVLs for this part. And in this problem, you do not have a KCL, but you have a resistor here, which you can write 1 Ohm's law as well. Okay, so let's go ahead and list what we can do here. Okay, so I would have 1 KVL on the left loop, and 1 KVL on the right loop, and also I have 1 Ohm's law. Yes, 1 Ohm's law. Okay, so let's go ahead and walk on this circuit and the direction of the current that is shown, IL. Yes, so if I walk on this circuit with the direction of the current that is shown, okay, you see that since I am moving in the same direction of the current, the voltage here across the inductor drops, okay, then somehow I get the positive polarity of E1, sorry, and I treat it just like the battery. Yes, I'm going to say that, okay, this E1, since I hit the positive polarity, the voltage drops, okay, and then from here to here, I hit the negative polarity of the battery again, it's going to be rising the voltage. Yes, so this is going to be negative EL, negative E1 plus ET equal to 0. Yes, so again, moving in the same direction of the current through I1, then hitting the positive polarity here, voltage drops for E1, hitting the negative polarity first here for E, voltage rises. Okay, let's do similar thing here. Okay, I'm gonna walk on this circuit in the direction of the current IC. Yes, so if you look at this, when you walk over R, the voltage drops because you move with the same direction of the current. Similarly, the voltage across this guy drops because you move the same direction of the current across the capacitor. And when you get to the second coil, okay, you see that you hit the negative polarity first, the voltage rises. Okay, so it's gonna be negative ER, negative ER, negative EC, plus E1, sorry, plus E2 equal to 0. The last thing that you can do is, is using the Ohm's law. Yes, for the Ohm's law, you guys know that ER, or the voltage drop across the resistor, is the value of the resistor multiplied by the I that passes through that resistor. In this problem, you notice that the I that passes through the resistor is the IC. Yes, so I'm gonna write it down as IC. Good. Okay, so just like the previous ones, you can go ahead and substitute for ER here. Yes, automatically it's going to be RIC here. Okay, and if you do that, you will end up with these guys. Yes, you will end up with negative EL, negative E1 plus ET equal to 0. Okay, and negative RIC, negative EC plus E2 equal to 0. Yes? Okay. Now look at this. There are a lot of things that are missing here still. Yes. I was looking for to rewrite EL in terms of my good terms, and IC in terms of my good terms. Yes, so they're my unknowns, but I have two other unknowns here, I1 and E1 and E2 as well. Yes. Okay. So it sounds like it's not helping me, these equations. Yes, in the first glance. Okay. However, if you look at the equations for the transformer, okay, you see that there is a relationship. Okay. I made a mistake here. Actually, it should be IL here. There is a relationship between IC and IL. Yes. And also there is a relationship between E1 and E2. So let's go ahead and use those two relationships, yes, in these equations. Okay. You notice that your IC is in fact equals to N1 over N2 IL, which since IL is a good term, your IC comes out as a good term as well. So here you can actually go back to equation cyclope and substitute for IC directly there. Yes. Also, you guys note that there is a relationship between E1 and E2. Yes. So E1 is in fact equals to N1 over N2 E2. So from the second equation here, you can solve for E2. Then substitute in this equation, find E1, substitute E1 here, and solve the first equation for EL. Yes? So let's go ahead and do that again. From the second equation, I'm going to solve for E2. My E2 is in fact equals to EC plus RIC. Yes? IC is not a good term, but EC is a good term. For IC, I'm just going to substitute the equation from the transformer. So this is going to be EC plus R1 or R multiplied by N1 over N2 IL. At this point, you see that this is a good term, this is a good term, and R multiplied by N1 over N2 is a constant number. So you were able to rewrite your EC in terms of your good terms. Yes? Okay. Now that you have this, go to the first equation, solve the first equation for EL. Your EL is in fact equals to ET negative E1. And you guys have a relationship for E1. What was a relationship for E1? It was N1 over N2 E2. Yes. So this is going to be ET minus N1 over N2 E2. Yes. And by the way, you have a nice right now equation for E2. Yes. And you can solve this one, substitute this one here as ET minus N1 over N2, all of it multiplied by the value for E2, which is EC plus R N1 over N2 IL. Yes, guys? Okay. Now look at this equation. This is your EL. Yes, that was the second thing that you were missing. EL, this is a good term. This is your input, constant number. We don't care about it. It's a good term. It's your dynamic variable, constant number. We don't care about it. It's a good term. It's your dynamic variable. So you were able to rewrite your EL also in terms of your, EL also in terms of your good terms. Yes. So let's call this equation as equation 2. Let's call the equation for the inductor here for the currents as equation 1. Okay. So by substituting 1 and 2 in equation smiley cyclope, okay, you can basically solve their problem. I'm going to start with equation 1 and cyclope since it's easier. Okay. So substitute equation 1 in Cyclop first, okay, you have C E dot C equals to IC, yes? So instead of IC, I'm going to put equation 1 from the transformer. This is a geometric relationship, yes? So this is going to be N1 over N2 IL. Good, okay. Now, bring all the dynamic terms on one side and check for the signs. If the signs match, you can box this equation, yes? So C E dot C equals minus N1 over N2 IL equals to 0, okay? And you see that you have only two families. Each family has only one member. You can safely box this equation. This is one of your equations. The other one is basically, you can find it by substituting 2 in equation smiley. So substitute 2 in equation smiley. You will have, instead of EL equals to, let's just bring it a little bit here, EL equals to L I dot L. Okay, instead of this guy, you can go ahead and substitute it from here. Yes, so by substituting 2 in this equation, okay, you will have you'll have such a representation for, let me just make it a little bit nicer, okay, for EL, okay, and the only thing that you need to do is you need to basically first make it a little bit nicer, yes, first multiply these terms here and here, okay, and then bring all the dynamic terms on one side and keep the inputs on the other side, okay, so if you do that, it's going to be ET equals to, sorry, ET minus N1 over N2 EC plus R N1 over N2 squared IL equals to L I dot L. Yes? Okay, and by just bringing all the dynamic terms on one side and keep the input on the other side, you will have ET equals to L I dot L plus minus R N1 over N2 squared IL plus N1 over N2 EC equals to ET. Yes? So at this point, I need to check for the signs. If the signs match, I can box this equation. If the signs do not match, then I need to go back and retract my steps to see where did I make a mistake. Yes? Okay. On the right-hand side of this equation, you see that I have two families, family of IL and family of EC. Yes? Within the family of IL, I have two members, IL and IL dot. And IL dot is positive here, but IL is negative. So I have a sign mismatch. Yes, I have a sign mismatch. This is the part that I need to be extra careful, because the signs of my family members do not match. So let's see, where did I make a mistake? Well, let's go to my KVLs first. For the KVL, I have negative EL, negative E1 plus ET equal to 0. Okay, then here it is fine. Here it sounds like to be okay. Okay, but from here to here, it sounds like to be okay. Okay, and then the rest seems to be okay. The only thing, the only part that I might have made a mistake is E2. Yes, so let's look at E2. For E2, I have negative RIC, negative EC plus E2 seems to be okay. Here, when I bring EC and RC to the other side, that seems to be okay. They are positive, yes. So here is positive also as well, okay. And all of these guys seems to be okay. Seems to be okay. Okay. And equation 2 seems to be okay. Now, when I bring equation 2 to the smiley, okay, then I would have, look at this. I would have positive, negative, basically EC. Then I multiply this guy, this negative, yes, is going to be multiplied by this guy, and I have it as positive. You see that? That's my problem. I need to fix that one. So this was a mistake. Why? Because when you multiply negative by positive, it's not positive. It should be negative. Now, when you bring this one negative to the other side, it's going to be positive. And it's going to solve my problem. Yes? Okay. And I can safely box this equation now. Okay. That's how I actually troubleshoot my model. I'm not going to box whatever I get. I need to check for the signs. If I made a mistake, I need to retract my steps. Yes? Okay. This is one thing. The other thing is, when we were talking about transformers, we talked about electrical transformers. We talked about 3 types of transformers. Okay. And we mentioned that we have step-up transformers, step-down transformers, and isolation transformers. For step-up transformers, they are the transformers that the number of windings on the second side is more than the number of windings on the first side. Yes? Okay. In a way, when you write down the equation for these guys, E1 equals to N1 over N2 E2, you see that if you rearrange these terms, okay, and solve it for E2, you see that E2 is in fact equals to N2 over N1 E1. Yes? So I just multiply everything by N2 over N1. Yes? And you see that if N1 is greater than N2, this number is greater than 1. Yes? So the voltage on the second side would be greater than the voltage on the first side. If you want to compare this, you can compare it with a gear chain that the number of teeth on the second side, so this is N2 and this is N1. Yes, the number of teeth on the second side is much higher than the number of teeth on the first side. Yes? So you can harvest bigger voltage on the second side compared to the one that you provide to them. Similarly, if you have a transformer and your transformer is a step-up transformer, okay, step-up gear chain, okay, you can harvest bigger torque here than the one that you provide. You provide a small torque here, okay, and you harvest a bigger one here. Okay. For step-down transformers, and also guys, notice that when the torque or when the effort or when the voltage increases on the second side, then your current is gonna decrease, just like the gear chains. Okay, if you harvest a higher torque on the second side, your angular velocity will decrease. For step-down transformers, we have the other way around. So your N2 is smaller than N1, okay? Which means that your E2 is gonna be less than E1. Yes, but again, when you decrease the voltage on the second side, your current increases, just like the mechanical gear chains. If you decrease the torque, your angular velocity increases. And then you have the isolation transformers, which is N2 over N1, okay, equal to 1, which means that the number of windings on the first side and the number of windings on the second side are the same. You will use these isolation transformers for safety reasons, okay, for connecting one side to the other side, okay, which means that you just put 2 transformers on 2 coils of wire adjacent to each other, that the number of windings are the same. So basically, you can isolate one part of the circuit from the other part with these transformers. Okay, I hope that this example was able to help you guys to understand transformers a little bit better and how you can actually use them in a circuit.